Okay, good morning, everybody, and welcome to this Severo Ochoa seminar. And it's a real pleasure that we have today with us Emilio Martínez-Pañeda, who's come all the way from London, from Imperial College in London. I hope that you're enjoying the weather. Although I was in the UK this weekend, and the weather wasn't particularly bad. But it's great to have Emilio with us in Sydney. Emilio is an associate professor at the Imperial College in London, one of the most prestigious institutions in the United Kingdom and in the world, particularly in areas of engineering. He's now an associate professor. And prior to being in Imperial College in London, he was also a fellow in the University of Cambridge, so quite a prestigious set of universities. His speciality and his topics of research range from many areas in computational solid mechanics, from ice sheets to microscale modeling of battery materials in batteries. Emilio has received quite a number of very prestigious prizes. For instance, the Spanish Society, the 70 Juan Seymour Prize, but also the Gustavo Colonetti Medal of the Wilhelm Society, the Royal Academy of Engineering Young Investigator Medal, and the UK Royal Academy of Engineering Young Engineer of the Year Award. I don't know what year, but I'm sure it was very, very recent. So it's a real pleasure to have you here. You can see the title of Emilio's talk, and over to you.
Thank you. Thanks a lot, Javier, and thank you for coming. Yeah, thank you for your kind introduction and also for your much appreciated invitation, Javier. It's really a great pleasure to be here. I cannot really emphasize enough how happy I am to be here today. So as a computational mechanician, of course, I have for a long time have a great admiration for the people in Sydney, and not only Sydney, but also the entire, I would say, Barcelona computational ecosystem. So it's really an honor to be here presenting my work. And what I want to present today is some of the work that we have been doing in three areas: this hydrogen embrittlement, lithium-ion battery degradation, and corrosion. Because these are three areas that I find particularly stimulating from a scientific perspective, but also because I think they're very important and relevant for society. And of course, this means that I'm going to try to cover a lot of ground, but these problems, they all have multiple things in common. One thing that they have in common is that the three of them are problems that are known to be difficult to simulate with computers. The three problems are coupled multiphysics problems, strongly coupled multiphysics problems that span multiple disciplines. They are interfacial problems in that if you want to deliver mechanistic predictions, if you want to resolve the physical processes of the problem, you need to be able to simulate moving interfaces. And there are also problems where the underlying material physics are complex, often multi-scale, and not very well understood. But I think there is an opportunity now to tackle these kind of problems, because we have computational technologies such as spatial methods that allows us to track moving interfaces. And we can also do proper multiphysics analysis. Computers are large enough that we can simulate multiple coupled fields. We know how to couple those fields. We can establish relationships between those coupled fields. And we can also take many of the things that we learn doing computational mechanics and bring them to other areas to develop models, for example, in electrochemistry or solid state physics. So I'll try to explain what I think we can do combining these two technologies. So before I start, something that is common to all of these problems is these spatial methods that I'll be talking about in detail today. So let me just briefly introduce them to start with. So the idea is computationally quite simple. So instead of having a sharp and discontinuous interface, you can smear that interface over a finite domain and then use an auxiliary variable, the phase field, to describe where the interface lies. So the phase field will take a distinct value in each of the phases, like a 0 in the blue phase and 1 in the red phase, and then it will vary smoothly in between. And then you just need to define a differential equation for the evolution of this interface equation, for the evolution of the phase field, and you're able to simulate interfacial problems of arbitrary complexity. So it's a very simple paradigm, but I think it has multiple computational advantages. Three that I always like to emphasize is that the interface equation is defined in the entire domain, so there's no need for any special treatment. That topological changes such as division or merging of interfaces can be naturally captured without any ad hoc criteria. And that is very well suited for multi-physics problems, because you can easily couple this interface equation with equations describing other physical phenomena. And in fact, I think it's fair to say that phase field has been a revolution in many areas of science and engineering. It all started in the condensed matter physics community, where phase field is by far the most widely used technique to simulate macrostructural evolution. It quickly gained traction in fracture mechanics. I think it is the most popular computational fracture mechanics tools these days. You can see here that you can capture very complex fracture phenomena, nucleation of secondary cracks, crack branching, coalescence of multiple cracks. And we have also recently shown that it can be used for corrosion. So we can use the phase field to describe how the corrosion front evolves. So the interface between the electrolyte, like seawater, and the metal, and how this changes. So I'm going to talk about that later on, but I'm going to follow this content of the talk. So I'm going to start first with hydrogen embrittlement, and then I'll tackle lithium-ion battery degradation and corrosion. And at this point, I should say that we are looking into these problems not only from a computational perspective, but also doing experiments. But of course, today I'm going to focus only on the computation side of things. So let me start with hydrogen. And the motivation comes from the energy transition. We know that hydrogen is going to play a key role in the transition towards net zero. We listen about it in the radio and the TV, we see it in the newspapers. And this is because hydrogen has the potential to decarbonize many applications and sectors, including some that are known to be particularly difficult to decarbonize, such as aviation or steel making. And I think the key to me is that this needs to happen very fast. So Airbus is saying that they're going to have hydrogen fuel airplanes in the air by 2035. The European Union is saying that they're going to deploy 40,000 kilometers of hydrogen transport pipelines in the next 10 years. So there's an urgent need to deploy a hydrogen energy infrastructure that currently doesn't exist. And this is a challenge. And this is a challenge because we know that hydrogen has a dark side. We know since almost 150 years ago that hydrogen makes metals very, very brittle. So you can see here, this was a paper of Johnson in the Proceedings of the Royal Society back in 1875. And he speaks about some remarkable changes in iron and steel due to the presence of hydrogen, some extraordinary decrease in toughness and breaking strength. And I mean, it's quite rare to see papers, particularly in those days, where words such as extraordinary or remarkable are used. But the way hydrogen interacts with metals is indeed remarkable and extraordinary. So one of the things that we see, for example, is a very significant reduction in ductility. So here we have metallic samples, dog-borne samples, uniaxial tension test. And you can see that if I expose my metallic samples to hydrogen, for example, by exposing them to hydrogen gas, then I get a very significant reduction in failure. Another thing that we see is a very drastic reduction in fracture toughness. So this is fracture toughness versus hydrogen content. And you can see that we go from 150 megapascals per meter to well below 40 megapascals per square meter to increase the amount of hydrogen. And this is for a low strength steel. But in high strength steels, the reduction in fracture resistance can be of up to 90%. And this is a key point to emphasize. The susceptibility to hydrogen damage decreases with the material strength. So here you can see fracture toughness for a given hydrogen concentration. So this is typical of exposure to seawater. And you can see that for very high strength steels, the fracture toughness in the presence of hydrogen is below 10 megapascals per meter. So metals become as brittle as ceramics. And this is important for two reasons. One is that what this is telling us is that hydrogen is compromised in decades of metallurgical research. So we have developed high performance materials, but we cannot use them. And the second thing is that we want to use high strength steels across many applications and sectors. And because they're more susceptible, this is triggering hydrogen assisted failures in otherwise very benign environments and in many applications where we never heard about this problem before. So traditionally, hydrogen was a problem related to aggressive environments, such as those relevant to offshore structures. But as we use these high strength, modern high strength steels in our bridges, in our buildings, in our railways, in our cars, we're starting to see hydrogen assisted failures in otherwise very benign environments. You can see here, just the hydrogen coming from the humidity or the manufacturing process is enough to trigger hydrogen assisted failures in one of the most famous skyscrapers in London. And of course, this brings me back to my main motivation. If hydrogen can change by orders of magnitude the fracture resistance and fatigue those rates in metals, how are we going to be able to deploy the hydrogen energy infrastructure that we need to achieve this decarbonization? And in fact, these are very early days. The technology is not even there, and we're already starting to see accidents happening. And what we need here is a model. If we had a model, that would be a game changer, because we will be able to not only prevent these catastrophic failures, but very efficiently and quickly map safe regimes of operation, so we could determine under which conditions we could deploy hydrogen energy. We could use the gas transport pipelines to transport hydrogen and so on and so forth. So there's a strong need for a model. But this is not an easy task. In fact, it's known as a kind of a grand challenge in materials engineering. And I think that there's two reasons why a model for predicting hydrogen assisted failure doesn't exist. I think one is that it is quite a complex physical process. So we don't really understand what happens. We know the basics. We know that hydrogen coming from any hydrogen containing environment, could be hydrogen gas or electrolyte or water vapor, will enter the metal. It will diffuse through the crystal lattice and it will be attracted to areas of high hydrostatic stress or high volumetric strains, where the space in the lattice for the hydrogen to accumulate. But then hydrogen interacts in this fracture process with the metal in multiple ways and at multiple scales, changing the dislocation mobility, changing the bonding strength of the metal atoms. So the physical picture is complicated. And the second reason why I think there's no hydrogen model out there is because this is quite a complex problem that crosses multiple disciplines. So you need to understand not only computational mechanics, but also chemistry, electrochemistry, condensed matter physics, and so on and so forth. So I'll tell you a little bit of how I tried to overcome those obstacles and how I tried to develop a computational framework for predicting these hydrogen state failures. And to me, the key was to try to resolve all the physical processes involved in the process. So only by taking a kind of a physically based mechanistic point of view, I was able to be confident on my predictions and be able to extrapolate on what's going to be able to happen. So I tried to resolve the physics involved in the hydrogen uptake process of ingress of hydrogen, in the transport of hydrogen within the metal, and also in the fracture process itself, in the breaking, the accumulation of hydrogen at critical interfaces, and the nucleation and growth effects. So let me tell you a little bit about it. So starting for hydrogen uptake. So here the goal is to develop models that are able to predict the uptake of hydrogen, so they quantify the ingress of hydrogen, for a given environment, what is the hydrogen content at the surface. And in gaseous environments, the picture is relatively simpler. So under certain assumptions and conditions, you can come up with closed form solutions that relate the hydrogen fluidity or pressure with the hydrogen concentration on the boundary. But in aqueous electrolytes, the issue is much more complicated because you need to resolve all the surface chemical reactions that are happening in the metal surface, and also the electrochemistry of the aqueous electrolyte, which can be very different in the bulk compared to the inside of the crack or pits or any other fluid electrochemistry. But I mean, we know what are the mathematics that describe, we know what are the mathematical theory that describes this kind of physical phenomena, so we can formulate PDEs and then we can solve them with a finite element model. So basically, this means that in the surface, you need to solve the hydrogen evolution reactions, so the Volmer-Horowitzky-Tafel and absorption reactions. And in the electrolyte, you're solving for the Nernst-Planck equations to be able to predict the concentration of ionic species and also changes in overpotential. And then, well, I'm not going to get into the details. You need to formulate all the reaction rates, but all these things depend on parameters that we can measure. They're all physical parameters. And then this is how your finite element model looks like. So you have an electrolyte domain where you're solving for as many ionic species as needed. Then you're also solving for the electric, for the electric potential. And then in the interface, you're solving for the hydrogen surface coverage. And then you have a metal, which may contain a crack, which you're solving for at the very least for the displacement and the hydrogen lattice concentration. So you can see that you can easily end up with 10, 12 degrees of freedom in your model, but luckily for us, computers can handle these things nowadays. And we have also developed computational procedures that can accelerate these calculations. I will mention that later on. And these are some kind of representative results. So this is for a given choice of applied potential. And you can see in the electrolyte a pH distribution. You can see that it changes quite drastically from the bulk to the inside of the crack. And then here you see the uptake of hydrogen concentration. And again, we can do this for different choices of material, for different choices of applied potential, for different choices of environment, for different defect geometries. We can use this virtual platform to predict the uptake of hydrogen under any condition and over any time scale that we're interested in. And then once you know how much hydrogen is coming to the metal, then you need to simulate the transport of hydrogen within the metal. So to be able to predict what is the distribution of hydrogen within your, say, industrial component. And the easiest way to do this is by using this kind of extended version of Fick's law, where you have hydrogen driven by gradients of concentration and also by gradients of hydrostatic stress. So this coupling with the mechanics is quite important. Hydrogen will accumulate in these areas of high hydrostatic stress. In fact, if you get the steady state solution of this problem, you will see that you end up with this exponential term here. So you have this hydrostatic stress inside of an exponential term. So you get a lot of hydrogen accumulated near stress concentrators such as cracks. But there's also one other thing that you need to take into account. Hydrogen not only travels freely through the crystal lattice, it's also sequestered or trapped at microstructural defects such as grain boundaries, carbide dislocations. So we have developed more sophisticated models that are able to account for this and that also introduce more couplings with the mechanics because your number of dislocations will change as you deform your metal. Anyway, once you know where the hydrogen lies, when and where, then you can predict the fracture. And here I'm going to make use of that phase field paradigm that I showed you before. And one of the things that I like about phase field is that it provides a computational platform for fracture mechanics. So the predictions are in agreement with conventional fracture mechanics theory. And this is something that I like because I trust fracture mechanics. Fracture mechanics is the what is the basis of our design standards. So it's very convenient that we have a computational tool that delivers what the engineers are hoping to see, and at the same time can handle very complex process. So just to provide a bit of context, so briefly, the father of fracture mechanics postulated that a crack will grow whenever the energy stored in the solid was sufficient to overcome the energy required to create two new surfaces, or the fracture energy. And you can postulate this into a variational form, but minimizing this functional is nasty because you have a crack and you don't know where your crack lies. So the idea is to use the phase field to regularize the problem. So this surface integral becomes a volume integral, and then you use the phase field as a marker. It's kind of like a damage variable, right? It goes from 0 in intermaterial points to 1 in fully cracked material points. And then it's kind of a non-local damage model. As you can see, we have gradients, so we have a length scale, and then it degrades the stiffness of the solid. You can get a good overview here by looking at the strong form of the equation. So the phase field will reduce the load current capacity. And here, this is a phase field evolution equation, where it's essentially a competition between the energy stored in the solid and the fracture energy and toughness, something that we can measure in the lab. And you can see here that just by solving this additional differential equation, you're able to capture very complex cracking phenomena on the original finite element mesh and without any convergence problems. All the results I'm about to show are Macro-Euler implicit calculations. Here you can see, for example, crack branching due to the application of a dynamic. And I won't say much into the phase. Oh, let me show you. Okay, so one point that I wanted to make with this picture is that I think that what I like about this method is that it's computationally very robust, it's easy to implement, and at the same time, it seems to deliver predictions in agreement with what we see in the experiments, based on this idea of building upon the thermodynamics of fracture and conventional fracture mechanics. You can see here multiple examples, some from my group, some from other groups, where you can see that very complex cracking phenomena can be captured and shown a very good agreement with experiments. And we have had quite a lot of fun through the years working on this. So we developed new phase field formulations for functional degraded materials, for the micromechanics of composites, for shape memory alloys, for glaciology to predict isobaric calving, for carbon nanotube composites. So we're having quite a lot of fun over the past 4 years working on this area, but I won't get into the details. Just one thing that I want to talk about is the solution schemes. So as you can imagine, there's two straightforward ways of solving this. One is what we call a monolithic approach. So you solve sequentially the displacement problem and the phase field problem. And this is good because it's unconditionally stable, but convergence is not very good because the regularized function is non-convex with respect to both displacement and the phase field. And the other approach, which is far more popular, is what we use a staggered approach, where you solve them sequentially, and people will typically use the single pass staggered approach, where you have the functional is convex with respect to the displacement for a fixed phase field and vice versa. So this is what people use, but then you lose this unconditional stability, so it's not ideal. And what we have suggested to do is to use a monolithic approach, but using quasi-Newton methods such as the BFGS. And this seems to be working very, very well. And I actually don't fully understand why. I've seen some of the mathematical literature where they show that some of these non-convex optimization problems, minimization problems, BFGS does a good job, but I still don't fully understand why. But it does work very well. Let me just show you with an example. So this is a classic benchmark in the phase field community. We have a square plate with a crack. This is a linear elastic solid, so the crack will propagate in an unstable fashion, mode 1 fracture. And this is the kind of force displacement result that you get. So you go all the way up, and then suddenly you get this sudden unstable crack growth event. So you lose all the load current capacity. And you can see that the monolithic is able to give you the right result with only 30 increments. So this unstable fracture problem, you can capture this in seconds in your laptop, while this kind of single pass staggered schemes require up to almost, I would say, 10,000 increments to be able to give you the right result. So this, of course, when you count for the number of total iterations, this means that you are using orders of magnitude more iterations when you're using these kind of staggered schemes versus this quasi-Newton monolithic approaches. So we find them to be very powerful, and we're very happy that we came across this. And we use this, for example, for simulations where we're doing fatigue, where we do cycle by cycle, and we really need efficiency, and this can make a big difference to us. Anyway, let me go back to the hydrogen. So we like to use phase fields. So we have, at the very least, in our problem, we have an equation for the formation of the solid, another one for the diffusion of hydrogen, and another one for the damage process. And I'm showing here some of the couplings, but the key coupling, of course, is how you interact hydrogen with the damage process. So we know, qualitatively, we know what we need to do, right? So we know that what hydrogen does is to reduce the fracture energy in the material, the fracture resistance. So we need to define a hydrogen degradation function. We need to just make this fracture energy dependent on the hydrogen content. But the key question is how to do that qualitatively. And there are multiple ways of looking at this. One way is, of course, you can fit it to experiments. And some of our industrial partners do this. They run multiple toughness tests versus hydrogen concentration, and then they have a relation that they can input for that specific material into their model. But I didn't want to present a model that was that require so much experimental calibration. My ultimate goal was to present a model that can deliver predictions just based on nominal material properties without any calibration whatsoever. So my plan here was to come up with a mechanistic hydrogen degradation function that incorporated the underlying physics. And I'll explain in a minute what is my idea, what is happening in there. But I think the good news is that this framework is universal. So whether you agree with me or you have other ideas on how to define this hydrogen integration function, you can always define this hydrogen integration function as a function of any micro or macromechanical parameter that you consider of interest. And other groups have taken our model and expanded it in other directions. But anyway, let me tell you what I think is the key hydrogen degradation function. And if you try to come up with a mechanistic interpretation of this problem, then I think the key question you need to answer is, how does hydrogen make metals brittle? How can it be that a metal that fails in a very ductile manner, as you can see here through micro-void cracking mechanisms, suddenly in the presence of hydrogen fails in a very brittle fashion with cracks originating along the grain boundaries? And to me, there's three things that are key to understand this. You need to think of the problem across multiple scales. The first one is that if you do atomistic calculations, DFT or molecular dynamics, what you see is that the surface energy or the fracture energy is very sensitive to the hydrogen occupancy. You can see here, if my interface, let's say a grain boundary is full of hydrogen, the coverage is equal to 1, then I get a 40% reduction in fracture energy. So this is the first ingredient. Hydrogen is going to make my grain boundaries much weaker. And then the question is, okay, but how much hydrogen do we have, right? Because if we are somewhere here, then, well, some of the mechanisms might be playing a role. And the answer to that comes from the experiments and from the thermodynamics of trapping. We can use what is called Oriani's equilibrium to relate the hydrogen concentration in the lattice with the occupancy of that interface, of that grain boundary, and with the binding energy, which is a property that measures how energetically favorable it is for the hydrogen to sit into that interface, that grain boundary, for example. And we know from the experiments that grain boundaries are strong traps with binding energies of around minus 40 kilojoules per mole. So you can see that as little as 1 part per million of hydrogen will basically make it, will basically fill my grain boundary with hydrogen. So it is energetically very convenient for the hydrogen to accumulate in those grain boundaries. So if we go back to the atomistic picture, this means that we're going to be somewhere here, and as a result of that, we're going to have a significant reduction in the fracture strength of the grain boundary strength. Another question is, okay, if you have a 30 to 40% reduction in grain boundary strength, is this enough to observe a transition from a ductile fracture process to a brittle one? And what we have seen, and I won't get into the details, is that when you resolve the stresses over the critical distance of the problem, which requires using some higher order strain gradient plasticity, what you see is that your stresses are not high enough to reach the cleavage strength or the grain boundary strength. But the moment you bring hydrogen into the picture, so that's why you need to have micro-void cracking mechanisms. But the moment you bring hydrogen into the picture, you lower this by 20 to 40%, and these two lines cross, and then you have a stall. You have a model that is naturally capable, without any ad hoc fitting parameters, capable of capturing that transition from ductile to brittle fracture just by simulating how much hydrogen you have and putting that DFT calculation in. And incorporating this into phase field is straightforward because we are solving the hydrogen diffusion problem, so we know how much hydrogen we have, where and when. We can use trapping thermodynamics to determine for that hydrogen concentration, how is the hydrogen going to be distributed in the microstructure, in my grain boundaries, for example. And then we just need to go to this DFT calculation that we run once in our lifetime offline, and then we can quantify how much the hydrogen reduces the fracture. So let me show you some representative results with this framework. One thing that I would like to say as well is that this is a critical crack growth problem, so we're not only interested in initiation of cracks, but also in the propagation, and therefore we need to be able to capture how, as the crack propagates, the hydrogen-containing environment follows. So imagine a pipeline in the middle of the sea. As the crack propagates, the seawater will immediately become in contact with the newly created crack faces. And we do this through a penalty approach, but of course there's multiple ways of doing this. So some representative results, these are R curves, crack growth resistant curves. So this is a measure of the crack tip stress, the applied load. This is the crack extension. And you can see, as you would expect from the experiments, that as you increase the hydrogen content, you lower your fracture resistance. This is another well-known experimental observation, sensitivity to the loading rate. So if you load your sample very slowly, then you let enough time for the hydrogen to accumulate in the fracture region, and therefore you lower your fracture resistance. But we can also be quantitative. This is a comparison with experiments on pre-charged steel bars. These are high-strength steel bars. And you can see that we get a very good agreement in terms of notch tensile strength and with experiments. So no fitting parameters whatsoever, and quite a good agreement there. And we can do more interesting experiments. So these are experiments done in Norway where they subjected multiple duplex stainless steel samples that contain a notch. They were immersed in a seawater bath to introduce the hydrogen. They subjected all of them to a constant load, each of them to a different load, and they measured the time to failure. And they were hoping that one of them was subjected to a sufficiently low stress that they would not see failure over relevant time scales. But as you can see here, all the samples fail relatively early, but we could take our phase-in model and not only reproduce their experiments, gaining confidence in our predictions, but also run virtual experiments with very large timescales. So we can determine what is this critical stress below which you can load your structures. And we can do anything, that's the beauty of it. So we can do standardized lab tests, but we can also do large-scale calculations that are related to we can also do large-scale calculations that are bring this idea of virtual testing to hydrogen containment. And more exactly, we can also couple this with inspection. So we can create sort of a digital twin of critical infrastructure. So you can see, for example, here, this is a 12-kilometer pipeline operated by BP that had multiple defects which repeating corrosion, all these red dots are defects. We can introduce those defects into a model. Remember, the phase-in is a degree of freedom, so this could be an initial condition on certain nodes in the phase-in, no need to have any functionalness. And then we can just load our pipeline to the in-service conditions, and then we can see how those defects eventually start growing, how they eventually merge with each other, and then how they eventually propagate and expand and introducing the complete failure of the pipeline. So I guess the takeaway that I want to say is that we finally have a tool that allows us to predict when hydrogen system failures will happen as a function of the material, the environment, and the loading conditions. And we can do that not only at the lab scales, but we can also deal with the large scales inherent to engineering practice. And we have also extended this to fatigue. So you can see here virtual SN curves where we can predict, I think in close agreement with experiments, both the predictions in the absence of hydrogen and incorporating hydrogen. And these are cycle by cycle calculations, which means that they're computationally heavy, but at the same time, they're very powerful in that we don't need to make any prior assumptions. We can predict the Paris law behavior without, as an output of the model, not as an input. We can predict, therefore, the role of hydrogen in accelerating fatigue growth rates, and we can deliver virtual SN curves for any arbitrary choice of loading conditions, loading history, geometry. You can see this is for notch, ion barrier. So I think this is computationally quite compelling and quite an interesting area to know. But anyway, let me move to the next topic, which is lithium-ion battery degradation. I don't think that this one is a lot of motivation. You are all familiar with lithium-ion batteries, but I think we all agree that we would like to have better batteries so we can have more durable laptops, phones, and also cars that can reach larger distances. And well, I think you're all familiar with how lithium batteries operate, but anyway, the basic thing to know is that whenever you charge your battery, you have lithium ions going from the cathode to the anode, and whenever you discharge the battery, you have lithium ions going from the anode to the cathode. And every time you have this, you have lithium intercalation within these storage particles, and this leads to some chemical strains and a swelling and shrinking of those particles. And when you do that over multiple cycles, what you see is that you get cracks appearing in those particles. And those cracks are arguably one of the main degradation mechanisms in lithium-ion batteries. So the reason why we need to change our laptops every couple of years. So we said, okay, can we use models again, this combination of multiphysics and phase refractor modeling to understand under which conditions we will see those cracks, how we can design better batteries. And a few people have done this. Well, let me just first say that the equations are actually not that different from the hydrogen case. I think there's only two main differences. One is that the toughness doesn't seem to depend a lot on the lithium concentration, unlike the case of hydrogen. And the other one is that this partial molar volume is much higher, it's an order of magnitude larger, which means that those chemical strains that are present in hydrogen but they're negligible become very relevant here. In fact, these chemical strains are where there's no mechanical load being applied here. It's just the lithiation and the lithiation which causes these chemical strains and therefore the appearance of cracks. And a few people have done this before. They have looked into phase-in models for electroparticle cracking, but they were only looking at one half cycle. But this is a cyclic process. So we added the fatigue contribution here, and we subjected this electrode to a sufficient number of cycles. So relevant to electric vehicles, we're talking about a few hundreds of cycles. And we looked not only to idealized particles, but also realistic particles that we can measure from X-ray CT scanning. And then we were able to deliver predictions again as a function of the particle radius, as a function of the charging conditions, as a function of the particle geometry, the location of cracks, and so on and so forth. So again, we have a virtual tool that allows us to predict over realistic engineering timescales when cracks will initiate, when those particles will crack, and how this will affect battery performance. So for example, we could determine what is the charging rate below which you don't see any cracking, or what is the particle size below which you don't see any cracking. And we have taken this one step further. This is together with colleagues at UCL who are very good in imaging facilities. So they have this very nice X-ray imaging facility. So we are able to model not only the particles, but the entire electrode. So we're able to capture what is the effect of the pores, of carbon binder, of the current collector, of the electrode thickness. So all these other secondary phases that also play a role. And again, computers are big enough, so we can do in both 2D and 3D. We can map those X-ray CT images, we can do segmentation, and then we can introduce this into our finite element model. And you can see here some 3D predictions of cracks evolving as a function of time. So we can see, for example, what is the effect of electrode thickness or the voltage window, and so on and so forth. Again, the same idea, using a virtual platform to accelerate the development of lithium-ion batteries, reliable lithium-ion batteries. And we have also taken this even one step further, where, again, building on these nice imaging facilities that these people have, we're looking into the microstructure of the particles, and we can see grain boundary, we're simulating grain boundary cracking as they observe in the experiments to be able to further understand how the cracks develop in these electroparticles, and whether we can, what would be the benefit of having single crystal electroparticles, which is now what everyone thinks will be a big difference in expanding battery performance. And I will say one more thing about batteries. This is a problem that I'm keeping me busy these days. So this is solid state batteries. So this is what people argue is going to be the next big disruption in battery technology. The idea is to replace the liquid electrolyte by a solid electrolyte, typically a ceramic. And if you do that, not only you gain safety because it's not any more flammable, but you can increase capacity by an order of magnitude. However, no one has been able to, well, there's some rumors going on, but as far as I know, no one has been able to commercialize a solid state battery. And the reason is that you have these mechanical instabilities happening. In particular, the problem is this dendrite, so these needle-like structures that generate at the lithium metal and then propagate all the way into the cathode, and then they cause the short circuit. And the way this works is as follows. So these are some very nice SEM experiments from the group in Oxford. Every time you have discharge of the battery, you have stripping. So you're removing lithium from the anode. And when you remove that lithium from the anode, you create these voids here. And every time you charge the battery, you have plating. You deposit lithium again in the battery and in the anode, and then you reduce the size of those voids. And understanding how those voids evolve is critical, because in the edges of those voids, we have what we call current hotspots. So regions where the current becomes very high. And as a result of that, in the next plating cycle, you deposit too much lithium and you get these dendrites that grow and short circuit could kill the cell, the battery. So we need to understand what is the current in those edges, and we need to understand how those voids fall. So again, a multiphysics problem that involves a moving interface. Not fracture anymore, but still a moving interface and a multiphysics problem. So we come up with a theory describing this physical phenomena and a computational model. And I won't get too much into the details, but these are, I think, the four main mechanisms. So you need to capture the interface reaction, so the lithium atoms being detached or during the stripping or put back in during plating. You need to capture lithium diffusion, the back-and diffusion, so you have solid state diffusion within the lithium metal. So this is a transport problem. We use a transport equation for that. You need to capture the voiding process, how those voids evolve, how they interact with each other. This is very suitable for phase field, of course, so you need to define a suitable phase field evolution equation. And then you have a lot of mechanics as well, because you have, well, first of all, lattice distortion due to these chemical strains, but also, most importantly, the main hypothesis in the battery community is that they will be able to solve all these problems by applying a stack pressure. So they apply a constant pressure, and therefore the creep and the deformation of the material will basically shrink those voids and eliminate the voiding problem. And what they don't know is exactly how much pressure they will need to put in there, and so on and so forth. So this is where the model comes into play. So you can see here the kind of boundary value problem and equation. So we solve a transfer problem, a phase field problem for scattering the voids, a mechanical problem with viscoplasticity, and also an electrical problem. We want to see those hot spots that we discussed before. So these are some representative results. This is a stripping. So on the left, you're seeing the lithium metal. On the right, you see the current, and I'm plotting phase field on the left, current on the right. You can see that the void kind of does what we saw in the experiment, so it expands, and you see those current hotspots there. So naturally, the model is able to capture the localized current near the edges of the voids. And this is plating, so it's the opposite effect. Again, we are depositing lithium, so we're seeing how those voids close, and even they become occluded from the interface, as we saw in those experiments. And of course, we are not only limited to model one void, but we can model more realistic conditions, multiple charge and discharge cycles with multiple voids. Again, trying different pressures, trying different cell geometries, trying different interface solutions to try to understand and come up with a new solid-state battery paradigm, I would say. So again, using this kind of multiphysics and interfacial tools to be able to predict what is the behavior and map safely into operation. So that takes me to one last thing. We have also very recently, this is in collaboration with Georgia Tech, we recently also used this to understand what is called anode-free solid-state batteries. And the model allows us to confirm what the experimentalists hypothesized, which was the fact that this first plating of lithium, the non-uniformity in that first plating of lithium is what makes all the difference in the development of this battery. So again, the model provides this kind of complementary insight that could be critical to develop this next generation. So that takes me to the last item of the talk, which is corrosion. And again, I don't think that this one needs a lot of motivation. Only in the UK, it carries a cost of £46 billion per year. So it's really a massive problem for society. You're all very familiar with society corrosion. And I think what is interesting about it, or what I find particularly stimulating about it, is that it's quite a long-standing problem for both scientists and engineers. We're unable to predict corrosion failures. And when you talk to the corrosion scientists, most of them will tell you that this is a too complex problem to simulate with computers. In fact, I would say 95% of the of the corrosion science papers are experimental, and the other 5% are DFT. No one thinks that you can develop a finite element model that can predict corrosion. And I mean, they're right to a certain extent. It is a complicated problem. There's too many things happening in there, and all these things are important. It's very strongly coupled. So let me just showcase, for example, corrosion fatigue of offshore wind turbines. And this is, by the way, the problem that limits the service life of offshore wind turbines. So we're working with Vattenfall and other industrial partners in trying to figure out whether they need to start decommissioning those offshore wind turbines, or they can let them there for a longer time. And basically, what you see is that first you have these peats, the nuclei at the interface between the seawater and the metal. Those peats start growing, driven by local chemistry and mechanics. And then eventually you get this peat to crack transition and the propagation of fatigue cracks. So I think there's basically two challenges here. First, you need to model, again, an interface that is evolving, that is complex. And the second thing is that this is a very strongly coupled problem, because the shape of those peats, the shape of that interface, will be driven by the local chemistry and mechanics. But the local chemistry and mechanics themselves are dependent on the shape of those peats. So we know that the pH will be very different inside of occluded electrochemistries and in small spaces. We also know that, of course, the sharper your peat, the higher the stress concentration, and that will also affect the corrosion kinetics. So everything is very strongly coupled, and you need to resolve all of these physical processes if you want to be predictive. But again, this seems like a good idea to use the phase field paradigm for. So it's a bit different than fracture mechanics, but it's kind of the same idea. So the phase field now describes the aqueous electrolyte metal interface. And I won't get into the details of how we formulate these phase field models, but they're closer to these solidification models that people use in the condensed matter physics community rather than the fracture mechanics ones. But essentially, in the easiest model that we have, so this is based on the KKS model. In the easiest model that we have two equations. One that describes the interface reaction, so the phase field simulating atoms detaching, so the corrosion process itself. And then you have another one that deals with the long-range interaction. So what happens with those metal ions that are detaching from the metal? Where are they going? The transport of those metal ions. So you have these two equations that you're solving for. And then when you're solving that, there's also a lot of mechanics that we'll discuss later, but when you're solving that, we can show that computationally, suddenly, you're able to capture pitting and stress corrosion tracking. And just to show you some representative results, there's some simple 1D problems that you can use to confirm that your model predicts the same as the analytical predictions. You can see that we get a very good agreement here. We can also compare with other computational studies, and you can see here, this is just avoid growing uniformly. There's no mechanical load here. But what I think is more interesting is incorporating these mechanic effects that can play a big role. And there's essentially two big mechanic effects here. One is that we know from a long time that mechanical fields enhance corrosion kinetics. So this is the corrosion current density, and you can see that it's enhanced by the plastic strains on the hydrostatic stresses. So we can incorporate them into our model because our phase field mobility coefficient, which was before a constant, can be quantitatively related to the corrosion current density. So we can define this phase field mobility coefficient as a function of those mechanical fields. And then we can benchmark our predictions comparing with those experiments on the C-ring test, where we can measure for different levels of applied load the propagation of corrosion defects. And you can see here that we get a very good agreement with experiments, both in terms of, I would say, qualitatively and quantitatively, both in terms of the size of the corrosion defect for different applied loads, but also in terms of, in terms of the corrosion morphology. So these two images are on the same scale, and you can see that we get a good agreement with experiments. We choose to model only one pit, but we can model multiple pits as well. And there's another important effect for mechanics. Very often, we have a passivation film that protects the metal from corroding. This is what happens, for example, in stainless steel. And therefore, your metal will not corrode unless you have mechanical fields that are large enough to rupture that passivation film, and then you get this kind of localized pitting and stress corrosion cracking. So at the end, it's a competition between, I would say, passivation kinetics and straining kinetics. So you have a situation where your corrosion current density is very high because your metal is unprotected. But then as you start passivating the layer, you start forming the layer, you bring down the corrosion current density until your strains are large enough and you rupture your passivation film and you're back again. So we can incorporate this easily again through this mobility coefficient, and therefore we can capture what is the effect of changing the stability coefficient, the passivation kinetics, the material itself, and we can capture this kind of, I would say, P to crack transition that people have been trying to predict for a long time. And just to say that, of course, because we're using phase field, we can capture problems of arbitrary complexity. So you could have, this is a funny academic experiment where you have multiple pits interacting with each other, and you can do that in 2D and 3D and so on. But I'll just finish by saying that I'm actually very excited about this particular field, because it is true what these people were saying, what experimentalists are saying. Corrosion is a very complicated problem. There's a lot of things happening in there. But we know what are the mathematics that describe, the PDEs that describe those physical processes. And finally, we have the tools and the computational muscle to simulate all those processes. So we can simulate corrosion from first principles, so to say, without any strong assumptions. So for example, you can capture here the effect of the electrochemistry. We know the electrochemistry plays a big role, but we can simulate the electrochemistry. We can capture the effect of the microstructural isotopy, not only on the mechanical behavior, but also on the corrosion behavior. We can capture also the effect of secondary unsuitable secondary phases. So you can see we capture complex corrosion process and even intergranular corrosion. And we can couple this with our previous formulations of fracture, fatigue, and so on and so forth. So just to provide some examples, we have extended those corrosion models to combine them with those hydrogen models. So very often, as a result of the corrosive reactions, you have hydrogen atoms coming into the metal. So it's very difficult to know whether cracking was driven by stress corrosion cracking or by hydrogen. Our goal here was to develop a generalized stress corrosion cracking model where we didn't have to make any assumptions. We just say, this is my material, this is my environment, these are my loading conditions. And you can see that the model is able to capture the behavior across a very wide range of environments and also the interplay between corrosion and hydrogen. We can also capture the effect of the microstructure. So we know from experiments that corrosion rates are sensitive to the crystallographic anisotropy. So we can define a grain orientation dependent corrosion potential, and therefore we're able to capture this different crystallographic anisotropy. And you can see here that this deviates from the kind of, I would say, mode 1 corrosion that you expect in an isotopic material. And again, you can also capture more complicated things like secondary phases and so on. We can also add all the electrochemistry. So again, you have the phase field for the corrosion problem. You may have a phase field of the fracture. You have the transport of solid ions, but then you also have this transport of ionic species. You also solve for the electrolyte potential and also the mechanical balance. So again, the problem gets big, but you are able to do it these days. So you are able to solve everything that is happening in there. And there you can capture, of course, how is the influence of the bulk concentration, how changing the applied potential or changing the bulk concentration, how changing the environment changes the corrosion process. And I think one thing that I want to emphasize here is that a lot of my electrochemical friends, they're starting to appreciate the influence of finite elements. But what my electrochemical friends are doing is they are downloading COMSOL. They are COMSOL uses symbolic differentiation, so they're writing the PDEs and they're getting some results. And I think that's very useful, of course, and those commercial packages can be very powerful, but they also have their limitations, of course. And we have seen that many of the things that we learned in our traditional computational solid mechanics can actually make a big difference in there. So I think there's an opportunity for people like us to create this area of, for example, computational electrochemistry and show that we can make a difference there. And this is just one example. When we were using COMSOL or any other commercial package, due to numerical oscillations, we had a lot of convergence issues because these PDEs can become very stiff because of the high reaction rates. So we were not able to get, it would take us a week in the supercomputer to simulate corrosion processes going over 10 minutes. And this, of course, is not, 10 minutes is not the time scale that we're interested in. But when we use LAMP integration, we could stabilize this much, much better. You can see here, this is the result of one iteration. You can see that this is very close to actually the real solution. And we are able, with these LAMP integration schemes, instead of Gaussian integration, we're able to predict over a week in the supercomputer corrosion processes that go over 50 or 100 years. And that is, of course, the time scale that we're interested in. So you can go from 10 minutes to 50 years. And this, to me, was an eye-opening. And I think now COMSOL is now trying to introduce this into their software. But again, there are opportunities for us, I think, and we can make a difference. We can also do other things. For example, all the experiments in corrosion and also the simulations, they all assume that you apply an applied potential because you don't want to wait 50 years for your sample to corrode in the lab. You want to accelerate the corrosion process. But there's no reason for that. I mean, in reality, this is not what happens. Very often, corrosion occurs in isolation. So we can take our model and instead of doing whatever COMSOL does, we can define the applied potential as a degree of freedom. We can impose this charge conservation equation, and then we can obtain what is the result, natural result of the metal potential, basically. And then we can see this is, by the way, work with Carmen Andrade, who is now also affiliated to SIMNE. So we can see what is the balance between the cathodic and anodic reactions. We can see, for example, how the corrosion current density depends on the concentration of oxygen, how as we run out of oxygen, the corrosion reaction can maintain itself through this current charge conservation with the cathodic reaction. So we can learn things about the physics of the problem, and we can simulate what I think is real conditions, which is something that one cannot do in the lab unless you want to wait for 50 years. And I think last but not least, this is we have also extended all of this to fracture and combined with everything that I presented before. So here we are interested not only in modeling the propagation of cracks, but also in seeing how the electrolyte changes within the crack. And this poses some challenges in the context of phase field models because we don't have a discrete crack, but the geometry of the crack is important for this kind of ionic transport processes. So we need to resolve that, and we have proposed new ideas on how to infer a crack opening from these phase field methods. And I think, one last slide. We've also extended this to the area of biocorrosion. So there's a lot of interest in using magnesium implants for magnesium alloys for implants because they will degrade naturally. So you don't have to do a second surgery to remove the implant, which is what they do in kids these days. But the problem is that magnesium degrades too fast. So there's not enough time for the bone or the tissue to heal while the magnesium is degrading. So people are trying different ideas like alloying or using composites. But of course, doing this trial and error is complicated and it takes a lot of time. But we can show that with our computational models, we can simulate those cases. And not only that, we can show that the model works under in vitro conditions, and then we can simulate with a model which are in vivo conditions, which is something you cannot do in the lab these days, at least in most countries. So that's all. I will just conclude, hopefully in time for a few questions with some high-level concluding remarks. The first one is that I think that the combination of this, I would say, computational technology, which is a space that allows you to track interfaces and multi-physics modelings are very powerful because you can finally kind of resolve by kind of brute force all the physical processes that are happening. So you remove assumptions, you finally have all the physics in place. And I think that I've shown that it's useful for not only fracture, but also boiling in solid-state batteries and also the corrosion. I think this area of patient corrosion is going to experience a revolution similar to what we have seen in fracture mechanics. And I think that these tools are also useful for society. I think we can make a difference in many areas relevant to the energy crisis. So we have shown that we can develop models that are able to predict the failure of metals exposed to hydrogen. We have developed models that allows us to map what are the regimes where one can achieve a breakthrough in solid-state battery technology. And we have also developed tools that allows us to predict over relevant timescales the corrosion of metals in aggressive environments. And I think as an engineer, it makes me proud to say that these tools are already having an impact on society. So there's multiple companies working with us in enabling virtual testing in hydrogen contained environments. So using these phase field models to predict whether we can transport hydrogen in natural gas pipelines, whether to design pressure vessels for safe hydrogen storage. We have also just started a big project now, a £2 million project with IMICA, which is the largest large-scale solid-state battery manufacturer in the UK, where they plan to use our model to develop the next generation of solid-state batteries. And also we're working, for example, with EDF in understanding the corrosion of nuclear waste canisters, because of course we need to be able to predict the corrosion of those nuclear waste canisters over very long time periods, and models can play a big role there. So I'm extremely happy with the outcome of this research project, and I think there's a good opportunity for people like us to make a difference in those areas. That's all. I will just finish by saying that all the codes that we use, we release them, so you can download them from our website and try and play with them and let me know if you have any issues. We mostly work with a variety of tools, some commercial packages, subroutines for our culture console, but also our own codes, Phoenix, our own codes in C++ or MATLAB, or even Adrià, who's sitting there at the back, was posted in the group working with Alia, and he comes from the Barcelona Supercomputing Center. So a wide variety of tools, we upload them all. You can download them and test them or calibrate them with your own codes and then continue from there. And of course, many thanks to all of you for your patience and to my sponsors. Thank you.
Very much, Emilio. If anybody has questions, please go ahead.
Emilio, thanks for this impressive presentation.
Thank you, sir.
In fact, to close the circles in a way, because phase field methods originated from the idea of materials who change the phases to discontinuous interfaces, and then they were applied to fraction, which is not exactly the same. You can back to the original situation, which you have two coupled interfaces, moving interfaces through moving interfaces materials and so on. So it's nice for the same tool can be applied in such a clever way to different problems. And that's general comment. So
Thank you very much.
I see this very general picture of computational mechanics methods to sort of different problems. And just more technical questions, Adeline, you mentioned that you had problems when using the algorithms for two different phases interacting with each other and so on, the stability of some of the numerical methods, and they use the BFGS method to solve that, which is also our experience as the problems become, or the algorithms become non-convex. The BFGAs require convex, theoretically convex algorithms that solve the instabilities that you apply for convergence and so on. However, in our case, you have applied the standard update using in BFGA's methods comes out in not always symmetric matrices, and that affects dramatically the convergence properties of that. So sometimes we have in the past we have applied some heuristic solutions to that, just artificially symmetrizing. That. Did you find some problems first? Second, how did you find it?
No, I actually never. It was a bit of a coincidence that we tried using this because it's already built in Java, so we decided to flip the button and see what happened there. And we never found any issues and it's working nicely, but I've seen other people that are trying to do it in their own codes, and they do say that you need to get all the ingredients right if you want to make it work. And I think you're right, you're hitting right in the nail. You need to have a symmetric positive definite matrix, and that's key. So sometimes often people say you need to combine it with the line search method. So there's some things that you need to be quite careful about it. Otherwise, you don't get those benefits that you need. But I think once you have everything in place, so far we keep throwing things at it and it seems to be working fine.
So you're using the algorithm in Abacus,
yeah,
which has its own ingredients, so to speak.
Yeah, I think it's I don't think they have any hidden stabilization techniques other than hopefully what they claim they do. And I heard from other people that have been able to do it in their own codes. But these people also told me that it's not enough just to have the standard BFGS. It's like one version of BFGS, and you need to probably couple with line search for some problems. So you need to have everything that Abacus happens to have in there to be able to get those benefits in there. Thank you.
Is there any other question? Comment?
Well, thank you for the talk. It's very impressive because you're doing what we all want to do, to have the right equations and by computational power and get the result. But what really strikes me as remarkable is that you, for these really stiff situations, very complicated interactions, the models work so well. My question is, have you found situations where the models were just not accurate enough and made everything not work, or why is it that they're such good models?
I think maybe the models, maybe I'm more optimistic than my postdoc PhD students, because when they come to my office with the results, then everything looks very good, but I'm sure they had to fight on the way. So it depends on the problem. Some problems do not work as well as others. So I think, I think the biggest issue that we were facing, for example, was the stiffness of these PDs when we were doing this electrochemical reaction with very high reaction rates. So this is where we came up with the LAMP solution. Before, we were kind of living with it. We would say, okay, we were going to learn what's going to happen in this corrosion process over 10 minutes. This is not going to tell us what's going to happen in 50 years, but it's going to give us some clues of how these things are working. And of course, many of these problems that we're dealing with, some of them we have 18 degrees of freedom per node. So they are becoming quite heavy. And of course, we have the supercomputer and things scale well, and you can do things these days with 18 degrees of freedom, but it's still, maybe we cannot do 3D for those specific problems, or maybe we cannot do very large time scales and so on. But so I guess I'm not really answering your question, but my answer would be some models work very nicely, others, due to the nature of the problem, they don't work so nicely. When we face those situations, we either are patient and just live with what we can, or what I think we should do more often, which we sometimes do, we apply our computational mechanics thinking and say, okay, we use this loop integration scheme, we're looking at cohesive elements. I think they can work here because then they couple the nodes and so on. So I think this is where we can make a difference to, the console users, so to say. So I think this is where, and I don't know if we do it enough, but this is the kind of thinking that and maybe sometimes you just need to live with it. But I think that there are algorithms and ways often to overcome those problems. And often it's quite, some of the problems that we're looking at, for example, the solid state batteries, this model has become very popular. A lot of people are using it, but still, I'm showing my results, but the convergence is quite tricky because lithium metal is like toothpaste. So it really deforms quite significantly. So you have very large deformations. You are removing a lot of material. So maybe an Eulerian framework will work better there. And so we probably should think a bit harder. So there's a lot of room for people to think harder from a computational perspective.
Still, when you get it right, it works. So,
Yeah, it does work for at least for certain regimes and timescales and so on. So far we're happy with what we got, but I'm sure it could be improved. Pretty sure.
Some last question?
Really, I think to me, this is like a new era of computational structural mechanics. I think this is really going to have an influence in many different fields, and I wish you best of luck. But I think this opens a great opportunity for all us to have an impact in many different industrial fields and also in bioengineering. So
Yeah, I think so.
great topic and great lecture. Only a practical last question, because you presented this as a very easy phase field as a very easy to use tool, but of course you have the problem of meshing. You never mentioned the word mesh or mesh adaptation, that is behind the method.
So we have,
and maybe for those of us, maybe for those who are listening to your lecture, and they're not aware that to implement this approach to get accurate results, you need a good mesh adaptation method. Is that true? Will you make a small comment?
yeah. So maybe in on your first comment, that I do think that this is quite an exciting area, and I think that some of these people, for example, electrochemists that are dealing with important battery products, don't have a training in finite elements. It's just not part of their undergraduate curriculum. So I think that's where I see the opportunity for us. And I also remember, your book was the first technical book I bought in my life, and I remember still that dam with the 20 elements drawing there. And I think we can finally do much more than 20 elements.
Last century or maybe 2 centuries ago.
So I think we're going. Luckily, we're getting enough computational muscle. This also connects with your question. So we have tried adaptive meshing, particularly using Phoenix. Also, Comsol has some adaptive meshing tools, but I didn't see that much of a benefit in that. I mean, it has a benefit, but it also carries some, you need to pay the price at some point. And many of our problems, it has reached the point where we can use brute force. So we could just say, okay, I'm not sure where this pit is going to go, where this car is going to go. You're right, we need to resolve the length scale. So we need to resolve the length scale of the problem. But we are reaching the point, particularly in 2D, where we could just say, okay, we just refine it all and run it in the HPC, and it will work. So it is something that is worth looking at, and it is a lot of people working on these adaptive remeshing techniques. And we have used some of them in the past, and they have worked okay. But at the same time, if a student comes to me, doesn't have the experience in there, doesn't have the time to spend it, I'll just tell him, okay, just do a brute force. And maybe this is not very clever, but it does seem to work.
And 2 years, okay.
Yeah, of course. In some cases, it becomes a bit more tricky.
Let me say that I think this is the right approach. So you use brute force wherever you can use it in order to see the method more itself. And then you can use specific methods like mesh, remeshing, or local meshing, and so on, if computers are not able to solve the problem. And I think that's right.
Maybe it's because I'm very patient. Maybe the students will appreciate how the results faster.
So I think it's time to finish the seminar. Let's thank Emilio again. See you all next time.